Are the attendants all from your university?
Yes, so some of them are my students, but we have also other attendees from the School of Engineering. So I sent the information of the talk to the School of Engineering. Some of them are from my research group. So we have a wide range of audience, undergraduate students. A lot of them are undergraduate students. We have graduate students. We have some faculty members.
Mm-hmm. Okay.
Okay, great. So I think it's 9:02 here and 10:02 in Georgia. So let's start. Thank you everybody for joining us today. Also, thank you so much, Dr. Song, for giving us a talk today. We are very excited to learn about your research projects. So Dr. Song is Georgia Power Mickey Brown Professor in Computer Engineering and founding director of the Center for Cyber Physical Systems at the University of Georgia. He also holds the courtesy appointment in UGA Computer Science and Statistics. He is a world-leading expert in pervasive sensing, computing, networking, and security, and has created and deployed various innovative sensor systems for health, energy, environment, and security monitoring. Dr. Song's research was featured in national media and received numerous awards and recognitions, including NSF CAREER Award, Outstanding Research Contribution Award, Chancellor Research Excellence Award, IEEE Mark Weiser Best Paper Award, and 3 times Most Promising Technology Awards from industry. Dr. Song served as the General Chair, TPC member, and Associate Editor of the most prestigious conferences and journals at Computer Science and Engineering, including IEEE INFOCOM, IEEE PERCOM, IEEE Internet of Things, ACM Transaction on Sensor Networks, and his research has been funded by numerous grants from the NSF, NASA, USGS, DOE, USDA, NIH, DOD, and industry. Thank you so much, Dr. Song, for giving us a talk today. I'm very excited to learn about your research. And to the audience, please feel free to send me your questions during the talk. And then at the end of the talk, either I will read your questions or read your name so you can ask your questions directly. Dr. Song.
Okay. Yeah, Dr. Taby, thank you for your kind introduction. And also very nice to meet everyone in the meeting. Okay, so as Dr. Taby mentioned, so I have been working on my research is specifically focused on sensor systems and sensor data AI stuff those days. So today it's my honor to present it to you my one of our recent research work on engagement-free and continuous health activity monitoring via passive seismic sensing. Okay, so my lab have been working on seismic sensor network, seismic sensing for many years. Virtually since my career, I have been working on this type of sensor. Basically, it's a geophone type of sensor. So in the past, we have been work on like earthquake, volcano monitoring with NASA, USGS, NSF. So we developed a system for like subsurface monitoring structure health. And over the past 6-7 years, we have been also explored another exciting area that is for doing human activity and health monitoring. I did have another line of research. Actually, we do the smart environment also for many years, we were using motion sensor in the past. But this seismic sensor does give more information, like for the human, walking activities, sleep activities, vital signs. All right, so today's talk, I'm going to just focus on one work of this sequence that is basically the BedDot. This is a sensor, you see on the picture. It can be attached. Basically, within there's a geophone sensor. There's a Raspberry Pi or computing board. It can be easily attached with the magnets on the side of the bed or under the bed. Okay, closer, kind of under bed. It does not touch human at all, and it is alternate powered, so it can, once you install it, no engagement is needed. Everything going to be automatically running. It's going to automatically detect whether someone is on the bed or not. If someone is on the bed, this sensor will automatically calculate vital signs, including heart rate, respiration rate, systolic and diastolic blood pressure. Okay. Also, we calculate interbeat intervals. So in terms of sleep activity, we can detect the movement, posture changes. Okay. All right. So this research has been, we have been funded by National Science Foundation, NIH and the GRA Venture Fund. We have got a variety of support, including like Center for Medtech Excellence in Atlanta, Georgia. So we also have multiple patent. Some is approved, some is pending. Okay, so the exact same sensor in the design, we have recently also make it work for seats, like under a chair with magnets attached to our chair, could also monitor vital signs and sitting activities, such as the cognitive status, emotion. That's something down the line. All right, we did, as I mentioned in abstract, we did also use the same type of sensor doing the floor activity monitoring, like check the trajectory or identify who is walking on the floor, how many people are walking on the floor, a fall down detection in our previous publications. And we use the same sensor, in fact, also use it for monitor animal activities. So two type of things I will not go to detail today, but basically you can imagine, a dog or cat put in the cage for at home or during the hospital ICU recovery. They need their vital signs important to be monitored. We also use the small animal like the rats, the mice, related to the drug vaccine development staff. So I'm not going to go that detail. I'm going to focus on the first one, the BedDot. I should mention this sensor with the envision, we can do a variety of health security activity, sleep monitoring research. So now let me come back to the BedDot. It's today's key focus of this talk. All right, so first, this is a BedDot system architecture. It's basically is a wireless sensor. It's sending data through Wi-Fi router to a cloud. Then it can be visualized in real time. Okay, and for this, in the bottom is basically showing a dashboard. This dashboard is actually could be done kind of, you can see it in, if I do a live demo, you can see those changes in every second. Okay, it will detect, as you see on the bottom here, it's those line basically showing this period, the people on bed, the people off the bed, then on the bed again. Okay, so the whole algorithm flow, I'm going to talk about, one part is related to signal quality assessment. That's including bed occupancy detection, also the movement. We need to know whether first step, I'm going to talk about how do you know this window of data does contain heartbeat or not, right? Because if there's a body movement, if there's nobody on the bed, it's impossible to calculate the vital signs, right? So the first step actually is about signal quality assessment or signal quality control. After we're sure make sure there is someone on bed and this person is there, so that we can start calculate the vital signs. Okay. All right. So give you a bigger picture about this the system. So here I'm basically showing the real data we captured in real time is heartbeat samples. So you kind of can see with eyes, you can easily tell there is heartbeat. Each one is a heartbeat, right? So if I further zoom in each heartbeat, you can see this one contains rich information. I wanted to clarify that this sensor, the signal, it's hard to say it's SCG or BCG. We kind of think that that does contain some features of SCG, some features of BCG, but they are not exactly the same. Because SCG, as Dr. Tabby group are also doing a lot of work on SCG in there, so SCG usually is a wearable or, traditional sense, right? It's a wearable put on the chest, while BCG is something under body, but typically still kind of touching the body, but ours is actually under the bed mattress. So there are more noise involved. Signal noise ratio is relatively lower than those standard SCG signals. All right. So let me, before I get into our algorithm, I wanted to kind of show you our vision and why the BedDot has a competitive advantage in certain applications. So first of all, fundamentally related my vision that IoT enabled daily health monitoring daily exam. Imagine that today, we usually do an annual physical exam earning, right? For health people, typically just 1 year, right? But imagine that if we could have those IoT device, not only BedDot, could be any other device, wearable or non-wearable, they are going to enable precise, personalized, and preventive care, health care, which is impossible today without IoT. Because today, usually you go to a medical clinic, you do one-time exam, right? But you don't know what happens in between. If we have this continuous monitoring every day, we could potentially, based on those patterns, the changes, to do some preventive cares. And I strongly believe that will be the future. Secondly, why BedDot? Why not just wearables? Why not just those, right? Wearables, smartwatch, iWatch stuff, right? This is related to another significant challenge. So we have been working with the healthcare industry. So one bigger challenge for them is like remote patient monitoring is engagement. Patient engagement is very hard. So if you try to tell the patient to remember charging your smartwatch wearable and wear it during your sleep, it's a hard thing to do. Some people for me, like me, I cannot wear a watch to get into sleep. I'm sure probably similar thing for many of you. And also to require like a person maybe with dementia or maybe autism, you wanted them to remember to charging it is also a difficult thing in reality. So that's why the barriers for wearable is mainly, maintenance, patient engagement. There does have other competitive technology for sleep monitoring. That's like sleep pads. It's a belt under the bed sheet or some sensors under bed sheet. Those sensors typically require you, the barriers mainly is, for example, the sensor typically needed to be under the heart area. Okay, if it's the sheet displaced or the weight bed sheets by enuresis problem or position misalignment, it's going to affect the system functioning. And another existing technology, as you know, is radar and a camera. So for I think I wanted to say every technology have their advantage, disadvantage. So not going, here I just want to mention that it's just for some people, like we talk to here, the elders, if I told them this is radar or camera, like going to give them every night in the evening, they're basically going to have a bigger concern on radiation or privacy concerns. So now let me show you to solve this problem. Now I'm basically moving on to the BedDot algorithm design. There is a significant challenges to overcome. So first I want to show you, even if you already got a good heartbeat signals, to extract the heart rate and the respiration rate is not a trivial problem. So later I will show you something when I get into details. Because imagine that those signal has been penetrating from your heartbeat. There is chest movement. It's going to penetrating the mattress, even the box under the bed, get into my sensor, the BedDot. So signal contain a lot of noise. This one is showing a clean heartbeat signal, sometimes not as clean as like this. Next, there are a variety of environmental noises, right? Even let's say, next page I will show environmental noise. Let's even show a normal people's activity on bed. They may be, nobody on bed, off bed, then sit on the bed, get off clothes, then lie down. The people maybe tends to move a little bit around. They maybe change postures, right? Then the sitting, get off bed. So the key thing, how do you identify each of them, right? Because bed occupancy detection is supposed to mean you need to know when the people are getting off bed and on bed. This itself have important application for elder care, because some elders, they get off the bed in the evening, go to the restroom. If they leave alone, they maybe fall on the floor, nobody knows. In fact, this is a personal story. This happened to my dad. So this is a very important problem. And the BedDot today could help us solve this problem. Now, let me show you more complexity. In real world, at a real home, there are going to be air conditioning will kick off, right? There may be some, walking activities, or maybe dogs running around, and all kinds of machine could be running, right? Washer and dryer machine could be running. They are going to generate those vibration noise, seismic noise. So the key thing, how do we, filter out them or identify that, maybe ignore this period of signals. Another thing I want to show you, as different people sleep with different posture, right? And with the back on left or right or chest, the signal are going to be changing also accordingly, right? Also, I showing you the variety of environmental noise like fall down, movement, sitting, jumping, dropping object, footstep. The footstep you see looks like a heartbeat. Okay, so how do you distinguish them from actual heartbeat? It's not trivial problem. So let me first show you, one of our design on signal quality assessment. So this one, we basically going to apply wavelength denoising at the first step, also do the score normalization. Then one thing we needed to do is to identify whether there's a person on bed or not. If there's a person on bed, we also needed to identify whether there's a movement or not. If no movement, people is there, then we extract the envelope. We need a smooth envelope, detrain the envelope, then do autocorrelation, then do spectrum and so on. Finally, we can be sure that's a good date for heart rate, for vital sign estimations. Okay, so beta occupancy detection is a non-trivial problem due to all kind of environmental noise you can imagine, or complex human activities. So the key challenge coming from including the following. First, inherent system errors of geophone is complicated direct person detection on bed based on amplitude earning. Okay, rely on solely on signal energy to detect has been proven to be could lead to cascading errors. Secondly, during the period designated as on-bed and off-bed, other vibration interference may occur, right? Could it be machines, air conditioning could kick on, right? Or washer machine could be running. All those things could affect it. So to address those first challenges, we have discovered some key features have good correlation of beta occupancy, such as zero crossing rate. Zero crossing rate has been widely used in voice recognition to recognize there is voice or not. So that's one thing. Another, we have identified a way to basically employ the kinetic energy changes between two consecutive timestamps that usually give better indicators to correlate it with beta occupancy. Okay. So later I'm going to addressing this problem again with deep learning. Here I'm just giving you some idea. We initially have basically used the advanced signal processing approach, try to identify the features that are correlated to beta occupancy. There are more stuff actually than what I just said in our paper. Okay. Now, movement detection. Here I'm showing you that you see this is heart rate on top of the picture. The bottom picture is showing the people is on bed, but there is movement. So we have discovered that, for example, we can use cursors as an indicator to differentiating those two type of signals. Now, let's move on to the heart rate estimation. So this problem to many people, maybe initially even from signal processing community, if they didn't work on much on real data, they were so that's a simple problem, right? You could just do FFT. You could find the dominating frequency, that is heart rate. And for many of us who work on real data, that's not a simple like that because a variety of noises. So what we did is we first do denoising. After denoising, we extracted the envelope of the signals, right? So for example, could use Hilbert transform. But after you got an envelope, you see the envelope still have lots of noises in there. So then we do another smoothing, okay? SG filter, we can do the smoothing. After smoothing, you would say, oh, this one looks already very good. I can easily just find the peaks and getting the heart rate. But do you notice that like this peak here, right? You almost see two peaks here. If you count the number of peaks, you might easily get it to, instead of 10, you got 11. But imagine that's 10 seconds. So 60 seconds, 1 minute would mean the error would be plus minus 6, right? So, but our goal is wanted to get the accurate heart rate, maybe with mean absolute error under 3. So you simply can't pick wouldn't work well, right? So what we did further is we actually applying two methods. One is autocorrelation function. Another, we also calculated the PSD, the power spectrum density. Anyway, combine those two, we could getting a more accurate heart rate. All right. So as I further explained here, if you simply count peaks, some signal, what we found is they are going to show the characteristics of SCG. You are going to see two peaks. So if you count those two peaks, wouldn't work easily. Even you do ACF, yes, they're going to see those two peaks. Okay. So it's non-trivial. I hope I convince you that this problem is not trivial. And more details, you can refer our IoT 2023 paper. Basically, the things we applying the leverage Bayesian fusion method on spectrum and ACF. That's how we calculate a more accurate heartbeat. Okay. All right. So now, built on top of the HR estimation, we further calculated the interval, basically the interval between the two heartbeats. And this one have important application for like AFIB and irregular heartbeat symptom problems, right? So the way to calculate this one is also non-trivial, but the basic idea is that, again, we do those one on top of the ACF of the envelope, not directly on envelope on the raw signals, because that's going to be very error prone. All right. So now let me move on to the RR estimation. R stands for respiration rate. Okay. So respiration rate is more. I mean, I shouldn't say more challenging. I mean, it's another challenging problem. So if you look at this good signal, right, with heartbeat, so where is the respiration? Let me find the, oh, this is a WebEx. I don't know how to do annotation. So let me just use mouse to show you. Oh, maybe I could do pointers. Let me see whether I can do highlighter, laser point of pen. Okay, so you can roughly see, if I draw this one, you can see there is up and down on top of the heart rate peaks. Do you see that? So that's basically is a respiration related, okay? But this kind of thing is not easy to get. So for example, if I'm doing like this one, as I showing earlier, to getting the, after we got heartbeat envelope, then do this purple line envelope. This is our PERCOM 2020, we did it that way, okay? But that time we tested on 20 people data. Recently, we did like 100 people data. This argument itself is not reliable enough, okay? So we did this approach. So how to solve this problem? What we did is we first do a wavelet denoising to mitigate the heartbeat interference. Then we also did the integral, basically doing the integral on the, remember the geophone data is velocity data, okay? Whereas SCG, by the way, SCG typically accelerometer, that's acceleration data. This one is velocity data. So velocity data, if we do integral, we will got the displacement data, okay? So this is basically the displacement data from this one, right? But from this one, you can see the system error going to accumulate. That's why you see a trend, a rising trend. So we need to remove the rising trend, basically doing a detrend. Then we got a so-called RRSG signal in our paper. After that, we can further extract the envelope of it. That's what we got. After that, we do smoothing, okay? Then we again apply the autocorrelation on each of those three signals. So here, if we just simply apply on one of them, the result not as good as we apply to all the three of them due to the errors on each stage, okay? By doing this way, we can get a very good heart rate estimation. Basically, later I will show you the result. The mean absolute error will be under 3, okay? So it's non-trivial to do that. All right, so the challenge behind our estimation is mainly due to, due to the respiration caused vibration is a no speed, basically means very low frequency, okay? The low frequency, in fact, is harder to deal with than high frequencies. So in seismology, right, those broadband seismometer is much, much more expensive than high frequency seismometers due to the same reason. So low frequency signal, in fact, is very hard for an instrument to capture them well, okay? Especially if we talk about a no cost system, right? All right. So also, further thing is that, basically what we try to show you here is we do those integration of to get the displacement signal. That's how we did it. Okay. Because respiration signal is better observed from displacement signal instead of the velocity signal. That's why we do the integration. All right. So now let me show you so over the past several years, in fact, the BedDot has been developed versus many versions, kind of we keep evolving, improving as we're doing more tests. So in the lab, initially, we basically using those oximeters, and also later we use the Apple Watch to do those study. Our previous student like Jose Maria and finally did a great job that they're doing a lot of intensive experiment off bed, sitting, then connected the data to do also the posture changes. So, and do the validation of the heart rate and respiratory rate. Also, this here is showing the respiration rate result. Now let me show you. I didn't talk about the 4 down stuff, but at that time, actually, my student Jose did a great job on he kind of simulating 4 off from the bed 480 times over many days. So just to simulating to find those events features, then do the machine learning to training it. All right, we also did the extensive field test. That's within our PERCOM 2020 paper. We have put the sensors on many homes and locations in Atlanta and Athens area to prove this algorithm. Okay, we use the ask the patient, the people are wearing the smart watch. Now, recently we have done as we further move on, because our goal is to make this device commercialized, get FDA clearance. So we have used the FDA cleared device called Caretaker 4. They have the heart rate, respiratory rate, blood pressure data. We used it for this clinical study of 100 people. There is 1 hospital bed and 1 family bed. We attach the sensor under the hospital bed and on the side. Also, on the family bed, it's very simple to install if you have beams. Basically, we have this installation board. Here I'm showing 4 of them, okay, just for comparison purpose. But normally you just need 1. Put it under there, just put it, that's it. So installation could easily take 1 minute to finish, okay? Now, here is the result showing on this picture, basically. So basically overall, okay, for the 100 people, we can show that our MAE for heart rate 1.38, respiratory rate 1.54, which is very good, right? And we also compared it, further did a deeper analysis with home bed. MA is this one, with hospital bed is 1.4. They're basically very similar, okay? Means the algorithm quite stable. In addition, we actually also did it with seats, with chairs. There were 25 subjects. We asked them to sit in between the hospital bed and home bed. So they are all very good. You can see RR rate is also pretty good, under 3, right? In addition, we further analyze what if the different sleep postures do they affect our accuracy? So like back posture, left, right, basically, stomach position. It's all showing good result. Stomach was actually the one more challenging. You see, this one is dragging the whole MAE a bit large. By the way, we also have some good preliminary results on the blood pressure. With this 100 people, we were able to achieve for example, for those 2 approaches, the systolic diagnostic MAE or under 5. Under 5 would mean meet FDA standard. The challenge we are facing with SBB, DBB right now is we needed to prove the algorithm does generalize to different population, different subjects beyond our test subjects. This is something we yet to do. according to FDA standard, requires 360 people. So we are working on that right now. And here I will further show you more deep analysis, like with here, what we're showing you is basically we show you the MAE, from 1, 2, 3, 4. A few does outlier does go above 4, right? But most of them you see below 3. I would say majority, right, is actually below 2 even. And okay, this is RR, same thing. We're showing most of them under 3, but a few be outlier, which is always normal, right? The IBI similarly, and this is the distribution HR radar, R radar, and IBI radar. We also did those bed occupancy evaluation at home bed, at hospital bed, or overall. You can see that this one, if you convert into percentages, this would be 90.99 percentage accurate. So to be honest with you, we actually hold a very high standard on bed occupancy right now. We are not talking about a percentage. We are not satisfied with 90.99 because we are more thinking from a user perspective. From a user perspective, if they use our BedDot, they likely would say that, okay, if I'm using your BedDot, your false alarm rate every week maybe should be less than 3 or less than 1 even. You see what I mean? So even if you every night you have one false alarm, this one false alarm, if you convert into percentage, would it be 90.99, right? But for user, they will not be happy. They will think, no, this system, I cannot trust it, right? Because it gives me false alarm every night. So this is something we are further improving. I may not have time to get into that. We are actually also combining deep learning approach to do that. But here, let me just show you one thing with the following 10 minutes. So we have done, actually recently submitted this paper to ICC. That is to generalize the HRR estimation from bed to chairs. By the way, here I want to clarify the previous algorithm I talked also does work on chairs also, okay? But here I will try to show you a methodology on deep learning. As you know, deep learning, a bigger challenge is that, how do you generate a generalized deep learning model, so-called domain generalization problem, right? Train on one type of, one group of subjects can't apply for a different group of subjects, right? So here I was showing you how we did it. So we are basically not just do a simple pre-processing. Basically what I mean is that the input to our deep learning model, here is a deep learning model, okay? Let me maybe first talk about deep learning model, okay? We basically use semi-supervised representation learning to do this job. We use contrastive learning here to basically given those signals, we are harder, HR signal, RR signal, we first augment the signals. Then we do with augmenting the signal, then you can do contrastive learning, right? Basically, if they are from the same signals augmentation, they should be the similar. If they are from different heart rate signals, they should be different. So with that, we're learning the representation features. Then those features will be used to do this same supervised representation learning, okay? Then do another supervised learning here without augmentation, right? Just this raw data here would be used to do the supervised learning, finally regress the HR and RR. Okay, and here is the model. So you may wonder what model we are using. We essentially using a kind of a ResNet TCN type of model within those encoder and the encoders. Okay, that's within the encoders. All right. So, so what's the input? As I mentioned, we are not directly using the raw data as input. So for harder rate features, we actually did those denoising stuff. Then use those denoised signal, then augment them. Here basically showing different augmentation like flip horizontally, flip vertically, scaling, and add a Gaussian noise to do those augmentation. For respiration signal, we basically doing the method I talked earlier. We first do find the envelope of the respiration, right? Then using this signal as an input to do the augmentation. Then those augmented signal, that's where it's showing on here as an input. All right. Okay. So here is the result from the from this evaluation. Basically, in here, I want to clarify, we basically collected more seat data. This one just focused on seat, on chairs, not on bed. Okay. So you see that this in a number 11 basically is the previous one we talked. With seat, we did more seat data. We did have this issue go above 3. But with this further refinement, we get reduce that one also under 3. Okay. So furthermore, we also did the ablation study under limited training data. Means we just use a subset of data, particularly maybe you see here is that we just use a subset of data, maybe 5% or 15%. Then you can see that even with basically earning like 5%, 15%, this one already drive the HRR close to 3. But certainly with this further, our algorithm refinement will reduce it under 3. Okay, here notice that the training data is from beds, not from seats. The test data is from seats. So there is a domain shifting from bed to chair. The materials are different, right? Second is different subjects. They are not same people. You see what I mean? So this is like a 2-domain generalization already. All right. So now let me summarize. I don't have time to talk about all the work related to BedDot. I'm just trying to show 2 pieces of work. So here, what we learned from the real world sensor system for in general, maybe specifically for health monitoring or physiological monitoring, data quality control is difficult but necessary and very important. So for our particular problem, we need to figure out whether there's people on bed or not first. Then, if people are on bed, we need to know whether the data quality is good enough for the heart rate or not. Right now, we are dealing with data quality for good for blood pressure or not. Those problems could be all different. Okay. Now, secondly, noise reduction and signal recovery is perhaps necessary as well. If you try to, unless you have unlimited amount of data, like those large language model, the video image stuff, but for sensor signal problem, typically you don't have that luxury data. So, you have to do noise reduction, recovery, even a lot of feature extractions, so that you can use a limited amount of data to training a good model. Okay. So we are currently, for example, thinking of some fundamental problem is how do you, given physiological signal like this one, is it possible from a window of data, you can generate a good single heartbeat signal such that this signal have very good high fidelity, right? Since in a short time period, everyone's heartbeat unlikely change much, right? For normal people, unlikely change much. So, and how to do that is a very interesting problem. Another thing, machine learning or deep learning, whatever, actually a fundamental problem is whether they did have invariant feature. if you did a non-invariant feature, then it's going to work on various environment, various subjects, cross domains, right? So as you know, today deep learning does show kind of very magical power. They can learn very complex features, work on some data maybe you cannot solve with traditional signal processing machine learning approach, but it does suffer a problem, so-called domain adaptation, domain generalization, or auto distribution problem, where essentially this is because they failed to non-invariant features. So there are a variety of methods in the community try to address this: congestive learning, optimal transport, and so on, right? But we are concerning about also whatever you do, is there do you have assurance? I mean, do you think you can interpret your feature you're learning? Do you have confidence level or a certain quantification of the method, right? So, we actually have tried many interesting experiments. We just use the synthetic data, okay, not real data, even just synthetic data. We know the ground truth, we add a noise. We have found that even the same deep learning architecture, they may fail to learn if I play with, for example, I just scale the data up and down. They are going to see, like this one basically showing a perfect trend matching learning. But if I just play with some unrelated features with the neighbor, you see what I mean? Then it's already failed to learn it. You see what I mean? So I think so deep learning is a black box. It has a problem. Random try doesn't need to reliable systems. And this is a well-known problem anyway, deep learning. So we try to also have students try to figure out this kind of fundamental problems. Okay. All right. So if finally, I wanted to acknowledge I have the privilege to work with many wonderful students and collaborators. They have done very creative works. So today I'm basically showing some of the work did by them. If you have interest, you can further dive into our papers. We also had the privilege to work with many health medical and groups on this proposed research. All right, thank you all. Any questions or comments?
Thank you so much, Dr. Song. Very interesting talk, and I enjoyed personally. We have some questions from audience, so I'm gonna ask a couple of them. One question that was also kind of in a different way. My question was that, let me read from that question. Many people have cats and dogs that live inside with them and often get on the bed. Is there a way for the BedDot to detect the difference between bed occupancy of a human versus an animal? And I'd like to add to that question, let's say if we have two people on a bed, can we use BedDot or let's say multiple BedDots, one on the left side, one on the right side, and then do some noise deduction to get all those vital signs from respiratory rate to heart rate from the signals?
Yeah, okay. Great question. Very good question. So first, regarding the animals like cats jump on the bed. So for this part, we haven't done this kind of experiment, but I can say that BedDot does able to detect the dog or cat's heartbeats, because we have, as I mentioned earlier, we does have another line of research, in fact, is doing that, is try to getting the, like for the example, this one actually is use heartbeats of ferrets, okay? So typically the animals, the way to differentiate them is the dog, the cats, this animal, basically smaller animal, their heart rate is higher. So for example, ferrets, a heart rate typically is between around 180 to 200, while human typically like 60 to 80s, right? So So I think this problem basically is solvable. We haven't, because doing this kind of experiment does require, as you know, you need to repeatedly doing those cat dog on bed to compare with. We just didn't have time to do that yet. Then regarding the two human problem, it's an excellent question. So at this point, BedDot is designed for single people on bed to get a reliable heart rate, respiratory rate. As you can imagine, so if there are two people on it, their signal basically going to be mixed up, right? They are going to have their two people's heartbeat going to showing on the signals. But one good news I can tell you is that we have recently tested with two people on bed. Even I will tell you, this setup actually is very challenging. Was a surprise to us because this bed is a king size bed. They have a thick mattress, thick box. We put one sensor under it with magnets, another one on the side. Actually, both of the two sensors was able to successfully detect the occupancy on bed, off bed. This one has successfully, reliably detected, which actually beyond our original design expectation. Okay, but for heart rate part, what we found is that our algorithm didn't double it. So it's maybe because we put the on the side of the bed, basically close to one person then another person. So the algorithm did still successfully calculate this single person's heart rate, right? So, but we didn't validate this actually test subject said that their respiration was also close to his respiration rate, which actually beyond my expectation. Now, but I'm thinking that this is something we needed to validate. We haven't done. Maybe with two people, even maybe with our existing algorithm already can detect the two people's heart rate. Okay, if we put a two BedDot, one on left side on the other on the right side, the reason is simply because the method we are using, we try to find the high peak. So you can imagine if there are two people on bed, the two BedDot on two sides, still always have one is higher peak than another. So maybe due to that. However, I cannot claim this one yet. The reason is we didn't do. Right now, I'm basically thinking that if I didn't do clinical trial with enough people, I cannot claim it. So that's the current state of the situation.
Great, thank you.
Yeah, thank you.
Another question interesting is that is there any way for BedDot to detect the differences between getting off the bed or falling off the bed? Let's say if for remote monitoring of, let's say, elder people in nurseries, is there any way that it detects getting off the bed to go, let's say, to restroom versus falling off?
Yeah, very good question. Okay, this is a great question. So here I'm showing you the fall down event, how this one simulated. Not simulated, I mean, my student simulated. Basically, he just fall down from bed to ground. The signature would look like this. You see this one, right? I have big event, then oscillates, and I got a small one. However, he did do this one in our PERCOM 2020 paper 3 years ago. But from my view on real world, I kind of very conservative to claim this result on fall down detection, because the reason is that I told my students that some people fall down isn't like what they're doing, suddenly fall down is what I mean. The elder people, they maybe slowly fall down. They hold on the bed or hold on the table, fall down. That kind of feature will be different. And as you can imagine, the difficulty part on AI stuff is that you just don't have those type of data on real world, then it's hard to claim that. So I basically conservatively think that today I cannot to do reliably detection between fall down. However, here is my justification. It's not as important. The reason is that if I able to successfully know the people is on off bed, it may be sufficient to give an alarm, alert to the caretaker. The reason is if elderly people get off bed in the evening, let's say go more than 10 minutes, didn't return on bed, that's potentially mean he or she maybe fall on the floor, on bathroom, not necessarily in the living or the restroom, the bedroom, right? So that may be enough for the bed occupancy. Basically, is enough to give an alert.
Okay, great. Thank you so much. There is another question again from the audience, and I had a kind of similar question myself. So they say, do you see this strategy of contactless collection of physiological signals extending beyond heart rate, respiration rate, and blood pressure? Let's say, for example, can we sometime in the future see that from your signals we can extract stroke volume, or let's say some of the cardiac time intervals, and then use them in order to even diagnose some diseases while someone is laying down on that bed?
Yes, okay, that's a great question. Yes, we have been thinking along this line as well. We actually, stroke volume, cardio output, also the AFib problem is in our interest. So right now, we if there's audience have the people have this kind of medical expertise, yeah, please contact me. I basically look for this kind of doctors, this medical background people to collaborate, because the key thing is data connection. So one thing why I think it's doable, again, is because of the data. We were able to see, since I can do blood pressure, I think likely we can do those cardio output, stroke volume stuff. AFib, you can imagine, is more straightforward because of interval. So those information does contain so-called systolic phase and diastolic phase. So we basically optimistic about that. We believe we can get this one work.
Great, thank you so much. So actually, Dr. Song, I will reach out to you because I think we may be able to help actually with what you just mentioned. I'm collaborating with some hospitals, and we are kind of trying to do something with SCG signals. So I think that would be perfect if we also attach your BedDot under the bed, and then since we are just collecting all that information, then we can try both SCG, and your signal, as you mentioned, is a combination of kind of maybe SCG, BCG. It doesn't look like BCG. It is something in between.
Yes.
So maybe we can just use both technology.
Yes. Thank you very much. Yeah, I would very lovely to talk with you. Thank you.
Thank you so much, Dr. Song. Thank you very much, everybody, for joining the meeting today. And if you have further questions, please feel free to reach out to Dr. Song. Thank you. Have a good day, everybody. Thank you again, Dr. Song.
Yeah, thank you very much. Thank you all.
Have a good day.
Good day.